The fundamental metric of the Bartlett Springs fault zone is 7.5 millimeters per year. That is the rate at which tectonic forces are driving deep crustal loading along a 100-mile structural line in Northern California. The system has maintained this rate of stress accumulation without undergoing a major surface-rupturing seismic event for centuries, quite possibly for up to a millennium. Capable of generating an event with a magnitude exceeding 7, the fault has ruptured the terrain in its prehistoric past. Yet throughout California's entire written observational history, it has remained completely unrecorded, operating in the background while scientific attention and hazard monitoring focused almost exclusively on the coastal San Andreas system. Now, the system displays markers of physical reorganization. A concentrated seismic swarm near the town of Covelo, accompanied by record-breaking ruptures on adjacent structural features, indicates a regional redistribution of strain. The central question for geophysical analysis is whether this silent component of the coast ranges is transitioning out of its long-term locked phase. The observational baseline shifted on a Friday afternoon in Northern California, shortly after 3 p.m. local time. In a remote sector of the coast ranges north of Covelo, seismic monitoring instruments recorded a sudden transition from background ambient noise to a rapid cluster of micro-earthquakes. Within hours, the sequence culminated in a magnitude 4.3 event at a shallow focal depth of approximately 5 miles. The proximity of the hypocenter to the surface allowed high-frequency energy to propagate directly into the local basin, causing noticeable structural shaking in Covelo. No pre-event warnings or automated mobile alerts were issued. The seismic waves arrived concurrently with the system's initial detection. From a structural perspective, a magnitude 4.3 event is not an exceptional load. The California crust regularly accommodates strain releases of this magnitude. However, the significance of a seismic event is governed not merely by its isolated energy yield, but by the physical characteristics of the fault structure on which it occurs. The Covelo sequence occurred directly within the northern reach of the Bartlett Springs fault zone, one of the longest, least understood, and most heavily loaded tectonic structures in the western United States. The background dynamics of the event indicate a broader cluster. Over the 12 hours preceding the magnitude 4.3 quake, the local crust experienced a series of preliminary events, including a magnitude 3.8 shock and multiple smaller tremors. This cluster matches the definition of a seismic swarm, a dense spatio-temporal grouping of events with comparable magnitude ratios, lacking a singular dominant main shock. Unlike a standard main shock-aftershock sequence, where stress drops rapidly following a primary failure, a swarm signifies continuous, multi-directional stress reaccommodation within a localized volume of rock. The Mendocino County sector had previously exhibited this behavior earlier in May 2026, when a pair of events, magnitude 3.5 and 3.3, occurred within a 12-hour window. To evaluate the operational limits of regional early warning networks, it is necessary to examine the wave propagation physics. Modern warning systems rely on detecting initial low-amplitude primary P waves near the hypocenter, calculating the event parameters, and transmitting data via electromagnetic signals ahead of the slower, higher-amplitude secondary S waves that carry the majority of destructive shear strain. This system creates a temporal buffer for distant population centers. However, for communities situated directly over the rupture plane, such as Covelo, relative to the northern Bartlett Springs fault, the spatial offset between the hypocenter and the receiver approaches zero. The P wave, S wave, and data signals converge simultaneously, eliminating any theoretical lead time. Furthermore, a magnitude 4.3 event falls below the energy threshold required to trigger automated mass notification systems. The absence of a prior alert was not a failure of detection infrastructure, but the mathematical result of physical distance limits combined with algorithmic threshold design. Analysis of the focal parameters confirms that the events occurred at a shallow depth of 5 miles. In deep crustal seismic ruptures, high-frequency energy dissipates over distance through geometric spreading and intrinsic attenuation before reaching the surface. Shallow hypocenters, conversely, transfer energy into the upper crust with minimal loss, producing sharp, high-acceleration ground motion directly above the fault plane. The Bartlett Springs fault accommodates strain within this upper, brittle crustal zone, ensuring that future large-scale ruptures will deliver unattenuated energy directly to local surface structures. Geographically, the Bartlett Springs fault zone trends northwest through the northern coast ranges, extending roughly 100 miles from the Cache Creek region and Lake Berryessa, past Lake Pillsbury, and through Round Valley near Covelo. It forms the easternmost major branch of the San Andreas fault system. While the primary San Andreas fault accommodates the majority of plate motion closer to the margin, the Bartlett Springs fault carries a substantial fraction of the regional right lateral strike-slip budget in parallel. The length of a fault plane dictates its maximum physical rupture limit. Empirically, the magnitude of a seismic event scales directly with the surface area and length of the active rupture plane. Short fault segments are physically constrained to low-magnitude releases. A continuous 100-mile structure possesses the surface area necessary to generate a magnitude 7.0 to 7.5 earthquake. The logarithmic nature of the moment magnitude scale means a magnitude 7.5 event releases approximately 31 times more energy than a magnitude 7.0. The Bartlett Springs fault zone possesses the spatial dimensions required to support an event of this scale. The remaining variable is the precise state of shear stress accumulation along its lock segments. The structural profile of the system contains a fundamental paradox. At the surface, portions of the fault exhibit steady fault creep, a continuous, non-seismic sliding motion facilitated by the presence of weak, hydrated phyllosilicates and serpentinite gouge. In localized areas, such as Lake Pillsbury, surface markers confirm a creep rate of approximately 3.5 millimeters per year. This behavior has historically led to the classification of the fault as a ductile, low-hazard safety valve that continuously bleeds off tectonic strain. However, satellite geodesy and precise surface deformation modeling demonstrate that this surface creep does not extend uniformly through the brittle crust. Deep beneath the lubricated surface layers, within the primary seismogenic zone, geodetic models resolve the existence of fully locked asperities, stuck patches that completely resist slip. While the shallow gouge slides smoothly, the deeper asperities hold firm, absorbing the deep tectonic loading rate of 7.5 millimeters per year. Far from mitigating the regional hazard, the surrounding surface creep acts as a strain concentrator, transferring shear stress directly to the margins of these lock zones and bringing the system progressively closer to its physical yield limit. Paleoseismic trenching data confirms that the fault is not permanently ductile. Subsurface excavations across the rupture zone have revealed buried structural offsets corresponding to at least 3 major prehistoric, surface-rupturing earthquakes. Radiocarbon analysis of the disturbed stratigraphic layers places the most recent major event between 300 and 1,000 years ago. Given California's written observational record spans less than 2 centuries, the fault's entire modern period of quiescence represents a continuous loading phase without a single major stress release. At a slip rate of 7.5 millimeters per year, a multi-century locking interval translates to several meters of unreleased potential displacement stored within the rock mass. The recent seismic activity near Covelo is not an isolated local event. It forms part of a broader regional redistribution of stress across Northern California's inland fault network. But to understand how a localized swarm can interact with a lock-deep asperity, it is necessary to examine the mechanism of stress transfer between adjacent fault systems and the unprecedented rupture that occurred directly next door. The interaction between adjacent fault systems is governed by the mechanics of Coulomb stress transfer. When a fault ruptures or shifts, it alters the surrounding strain field, increasing shear stress on neighboring structures that are aligned with the new stress orientation. In late June, a significant seismic event occurred on the secondary fault network immediately adjacent to the Bartlett Springs zone. This event represented the largest earthquake recorded on that specific structural segment in 75 years. It serves as a direct physical baseline for evaluating how stress migrates across Northern California's complex inland plate boundary. The regional tectonic budget of California is driven by the differential motion between the Pacific and North American plates, moving past one another at an average rate of roughly 50 millimeters per year. While the main coastal strand of the San Andreas fault accommodates the primary share of this translation, up to 25% of the total plate motion is distributed further inland across the coast ranges and into the Walker Lane belt. The Bartlett Springs fault zone operates within this inland shear network. It acts as a primary conduit for strain that cannot be accommodated by the coastal faults alone. A common superficial interpretation of regional geodynamics assumes that individual faults operate in isolated silos, where an earthquake on one structure has no physical bearing on its neighbors. Systems analysis demonstrates the opposite. The crust functions as an interconnected stress continuum. When a localized segment experiences slip, the accumulated mechanical strain does not vanish. It is redistributed through the surrounding rock mass. If an adjacent fault segment is already loaded close to its frictional failure threshold, even a fraction of a bar of positive stress change transferred from a neighboring rupture can be sufficient to trigger a secondary failure. To evaluate the human factor and local infrastructure vulnerability, one must examine the specific topography and settlement patterns of Round Valley and Mendocino County. Unlike major metropolitan centers engineered to modern seismic building codes, the communities situated directly atop the Bartlett Springs fault zone rely on older, unreinforced structures, rural power grids, and isolated transportation corridors. A major rupture along the 100-mile extent of the fault would not merely generate severe ground shaking, it would cut off primary access routes through mountain passes via widespread slope failures and landslides. The physical reality of a shallow, magnitude 7 class rupture in this topography is the immediate isolation of the local population from emergency infrastructure. Furthermore, a prevalent public misconception holds that frequent minor earthquakes serve as a harmless release valve that prevents larger events. This safety valve narrative fails under basic energy budget calculations. Seismic energy scales exponentially with magnitude, governed by a factor of roughly 32 for every full unit increase on the moment magnitude scale. It would require over 30,000 magnitude 3.0 events, or approximately 1,000 magnitude 4.0 events, to release the mechanical energy equivalent of a single magnitude 6.0 earthquake. To release the energy of a magnitude 7.5 event, the upper physical limit of the Bartlett Springs fault, it would take tens of millions of small shocks. The background microseismicity and localized swarms recorded near Covelo are statistically insignificant in terms of total stress relief. They do not drain the system, rather, they signal that the rock mass is actively fracturing under sustained mechanical loading. At the microcomponent level, the mechanical state of the fault zone is determined by the friction properties of the fault gouge inside the core of the rupture plane. The transition from continuous, non-seismic creep to unstable, sudden slip depends on whether the gouge material exhibits velocity strengthening or velocity weakening behavior under pressure and temperature conditions at depth. In the shallow crust down to 3 miles, hydrated minerals facilitate steady sliding. However, at depths between 5 and 12 miles, where temperatures exceed 100 degrees Celsius and lithostatic pressure seals microcracks, the rock transitions to a velocity weakening regime. Within this zone, once friction breaks, the resistance drops instantly, causing rapid rupture propagation at speeds exceeding 2 miles per second. The lock disparity identified deep beneath the Bartlett Springs fault zone sits squarely within this unstable velocity weakening depth window. The shallow surface creep that has been measured for decades at Lake Pillsbury is merely a thin, ductile skin overlying a rigid, stress-accumulating core. By treating the superficial creep as evidence of total system safety, past hazard assessments overlooked the continuous loading of this deep mechanical core. The convergence of historical silence, multi-century strain accumulation, deep lock disparities, and recent localized swarms creates a clear analytical profile. The system is operating at or near its mechanical limits. The critical question shifts from whether the Bartlett Springs fault holds sufficient energy for a major rupture to how the ongoing regional stress redistribution will force the locked core to its final yield point. The fundamental metric that defines the current state of the northern coast ranges is the unreleased displacement budget. Across the 100-mile geometry of the Bartlett Springs fault zone, a slip accumulation rate of 7.5 millimeters per year, operating over a 300 to 1,000-year locking interval, yields a cumulative displacement deficit ranging from 12 to over 24 feet. In geophysical terms, this deficit represents stored elastic strain energy held within the brittle crust. When a lock disparity fails under this magnitude of stored strain, the resulting dynamic rupture does not propagate smoothly. It releases centuries of accumulated shear displacement in a matter of tens of seconds. To understand the systemic risk, one must trace the physical cascade from deep lithospheric driving forces down to surface infrastructure. The Pacific and North American plate boundary is not a single clean mechanical line, but a broad deformation zone spanning tens of miles across Northern California. While public perception remains anchored on the coastal San Andreas, the inland Bartlett Springs fault zone anchors the eastern margin of this deformation belt. The inland structural network absorbs a critical share of the total strain budget, operating as a parallel engine of regional deformation. The deconstruction of regional hazard models reveals a significant historical blind spot. For over a century, public safety frameworks and institutional focus were concentrated almost exclusively on populated coastal fault segments. This geographical bias created a false sense of security regarding inland structures. Because the Bartlett Springs fault traverses thinly populated forest terrain, cattle ranges, and isolated mountain valleys like Round Valley, its lack of historical surface ruptures was casually interpreted as inactivity. However, physical hazards hazard is dictated by fault dimensions, slip rates, and mechanical strain accumulation, not by surface population density. A magnitude 7.0 or 7.5 earthquake on an inland structure generates identical near-field ground accelerations, regardless of whether it strikes beneath a major metropolis or a wilderness valley. At the micromechanical level, the transition from quiescence to dynamic rupture along a partially creeping fault is driven by stress concentration along the boundaries of locked asperities. As the shallow, serpentinite-rich sections of the fault experience steady surface creep at 3.5 millimeters per year, they continuously deform the surrounding rock mass. This differential displacement does not relieve systemic tension. Instead, it sharpens the stress gradient directly along the perimeter of the deep, velocity-weakening lock patch. The creeping zones act as mechanical levers, focusing strain directly onto the stuck core. When this localized stress concentration exceeds the frictional shear strength of the lock gouge, microfracturing accelerates. This process is recorded by monitoring networks as localized seismic swarms, such as the sequence observed near Covelo. The clustering of shallow, magnitude 3 and 4 events represents the localized failure of small structural barriers around the perimeter of the main lock patch. Rather than signaling a harmless release of energy, these swarms indicate that stress is migrating and probing structural weaknesses across the fault plane. The systemic consequence of a full segment rupture on the Bartlett Springs fault involves severe physical disruption across Northern California. The high-frequency seismic energy radiated from a shallow 5-mile hypocenter would generate extreme ground motion capable of destabilizing steep mountain slopes across the Mendocino National Forest. Mass wasting events and rockfalls would sever vital transportation corridors, isolating inland communities like Covelo and blocking emergency access routes. The destruction of regional utility lifelines, combined with secondary slope failures and ground deformation, would effectively disconnect the interior valley infrastructure from the rest of the state. The recorded data from the Covelo swarms, combined with paleoseismic trenching records and geodetic satellite measurements, presents an unambiguous physical conclusion. The Bartlett Springs fault zone is a fully active, structurally mature, and heavily loaded continental fault system operating at the tail end of its historical strain accumulation cycle. The long-term silence of the silent giant of the coast ranges was never evidence of stability, but the quiet accumulation of a massive energy debt. The system is actively signaling that its multi-century period of quiescence is drawing to a close. The physical integrity of Northern California's regional infrastructure is fundamentally calibrated against the historical record of known coastal earthquakes, leaving a critical structural vulnerability to inland ruptures. When evaluating the systemic threat posed by the Bartlett Springs fault zone, the analysis must shift from the isolated behavior of a single fault trace to the domino effect of regional failure dynamics. A major rupture along this 100-mile inland corridor does not occur in a vacuum. It directly impacts the adjacent faults, local topography, and the fragile lifelines connecting mountain communities to the broader state grid. At the macrostructural level, the Bartlett Springs fault zone is mechanically coupled with neighboring fault strands in the northern coast ranges, including the Lake Mountain Fault and the Calaveras-Concord system further south. As strain builds along the locked, deep asperity of the Bartlett Springs fault, the entire regional crust undergoes subtle, continuous elastic bending. Geodetic satellite observations confirm that this regional warping extends across tens of miles, loading parallel fault planes simultaneously. When the primary locked core of the Bartlett Springs fault reaches its physical yield point, the sudden release of several meters of slip will instantly redistribute static and dynamic stresses across the surrounding crustal volume, potentially triggering secondary ruptures on adjacent parallel structures. This mechanical coupling deconstructs the persistent superficial myth that inland California is sheltered from major disaster scenarios due to its lower urban density. While the density of high-rise structures is minimal compared to the San Francisco Bay Area, the critical vulnerability of the interior region lies in its low infrastructural redundancy. Modern urban networks rely on multiple redundant highways, power lines, and water conduits. In contrast, the interior valleys, such as Round Valley and the surrounding terrain of Mendocino County, depend on single, highly vulnerable supply corridors carved directly through steep, geologically unstable mountain passes. The human factor in this geophysical equation is defined by this extreme infrastructural isolation. A shallow magnitude 7.0 to 7.5 earthquake, originating 5 miles beneath the Bartlett Springs fault zone, would subject the surrounding mountains to violent, high-acceleration ground shaking. The steep, oak-studded ridges and weathered sedimentary rock masses of the coast ranges are highly susceptible to co-seismic slope failure. Hundreds of simultaneous landslides and rockfalls would bury state routes, collapse mountain bridges, and sever overhead power grids and fiber optic communications. Under these conditions, rural population centers like Covelo would experience instant spatial and operational isolation, cut off from external medical, fuel, and emergency support for days or weeks. At the micro scale, the physical mechanism driving this catastrophic potential remains anchored in the thermal and mechanical behavior of fluids inside the fault core during fast slip. As a locked asperity begins to fail, extreme frictional heating rapidly pressurizes trapped pore fluids within the low permeability fault gouge. This phenomenon, known as thermal pressurization, dramatically reduces the effective normal stress holding the fault planes together. In effect, the fault becomes hydroplaned by its own superheated pore fluids, causing the coefficient of friction to plummet near zero within milliseconds. This rapid drop in frictional resistance allows the rupture front to accelerate rapidly to speeds near the shear wave velocity of rock, radiating intense, destructive high-frequency waves toward the surface. The data gathered from the Covelo seismic swarms, the 3.5 mm annual creep at Lake Pillsbury, the deep 7.5 mm loading rate, and the centuries of unreleased displacement budget all converge on a single physical conclusion. The silence of the Bartlett Springs fault zone was never a sign of safety, stability, or permanent creep. It was the slow, silent accumulation of a massive mechanical strain deficit inside a continuous continental shear structure. The quiet giant of the Coast Ranges has spent California's entire recorded history holding its breath. The recent seismic activity signals that the structural limits of the system are being tested, and the long-deferred energy debt of Northern California's most dangerous unknown fault is approaching its final accounting. The dynamic response of the Bartlett Springs fault zone to regional stress accumulation establishes a strict physical boundary on what modern monitoring networks can mitigate versus what local geology dictates. The existence of high-precision instrument grids across California has fostered a public expectation that technology provides a virtual safety net against seismic hazards. However, the operational constraints of seismic networks exposed during the Covelo swarm highlight the absolute limits of human technological intervention when confronted with deep crustal failure mechanics. Instrumentation and satellite geodesy allow scientists to observe the system with unprecedented clarity. Seismometers track microfractures, radar satellites measure millimeter-scale deformation from orbit, and geodetic models successfully isolate the position of locked asperities deep within the seismogenic zone. Yet, this high-resolution observational capacity does not alter the underlying mechanics of strain accumulation. Watching a loaded fault twitch in real time provides diagnostic data, but it cannot slow the 7.5 mm annual deep loading rate driven by global plate tectonics. The technology acts as a witness to the process, not a control mechanism. When evaluating the human factor in disaster preparedness, a dangerous cognitive dissonance emerges between technical risk assessments and public perception. Because the Bartlett Springs fault zone has remained absent from the written historical record for nearly 2 centuries, regional planning and public risk awareness have consistently prioritized coastal structures. The physical reality, however, is that tectonic systems operate on geologic timeframes that render human historical memory statistically irrelevant. A fault system that has accumulated up to 24 feet of unreleased displacement across a 100-mile structure will eventually resolve that mechanical imbalance according to the laws of friction and elastic strain release, irrespective of human calendar expectations or municipal readiness. The physical limits of the system are absolute. The locked patch buried within the Bartlett Springs fault zone represents a finite mechanical barrier holding back a vast energy budget. The continuous shallow surface creep recorded at Lake Pillsbury, far from neutralizing the threat, acts as a steady vector concentrating shear stress directly onto the edges of this stuck core. Meanwhile, localized seismic swarms near Covelo confirm that stress is actively migrating through the surrounding rock volume, testing structural limits, and breaking minor asperities along the margins. If the system reaches its ultimate yield strength, the resulting rupture will release centuries of stored energy across a major continental strike-slip structure. The immediate physical consequences, violent near near-field ground accelerations from a shallow 5-mile hypocenter, extensive co-seismic landslides across the northern coast ranges, and the sudden physical isolation of mountain communities in Round Valley are the direct mechanical outcomes of a shallow, highly loaded fault line breaking through the brittle upper crust. The ultimate takeaway from the deconstruction of the Bartlett Springs fault zone is a sober lesson in systems analysis. Nature operates through strict energy budgets, mechanical load limits, and structural stress balances. The long-standing silence of Northern California's remote inland giant was never a promise of permanent stability, nor was its shallow creep a sign of harmless energy dissipation. It was simply the quiet, relentless loading of a continental-scale spring. The instruments are active, the data is documented, and the physical limits of the rock mass are fixed. The Bartlett Springs fault zone is an active, mature, and heavily loaded tectonic engine, patiently waiting out its long cycle in the quiet mountains of the coast ranges.